So a gram of uranium has 20 billion calories. What would happen if I ate a gram of uranium? Apart from the radiation, you'd get probably lethal heavy metal poisoning.
You'd die.
You would get radiation poisoning. There are two types of calories. There's lowercase c calories. This is the amount of energy it takes to raise the temperature of 1 milliliter of water by 1 degree Celsius. Then there's the kilocalorie or uppercase C calorie. That's 1000 lowercase c calories. The kcal is the one most commonly used when discussing nutrition, and that's based on how much of that energy our bodies are able to take out of the food consumed. Uranium is not a super dense food and your body can't utilize those calories. When it's said that a gram of uranium has 20 billion calories, it means that it contains enough energy to heat 20 billion milliliters of water by 1 degree Celsius. Death from heavy metal poisoning. As for energy release, your digestive system is not a nuclear reactor and thus won't be able to extract any of these 20 billion calories. If dark magic releases 20 billion calories inside your body, you will get vaporized, as will quite a bit of ground that you are standing on. Actually, uranium has 0 calories. The calories you quote for uranium come from nuclear fission, not from a chemical reaction. Therefore, to your body, the uranium has no caloric value. As to what will happen, it depends on the isotopes of uranium in the sample, but you will not have a good week. It will either be radiation poisoning or heavy metal poisoning. I don't know what the thresholds are exactly for expecting to die by either radiation poisoning or heavy metal poisoning. Either might be a factor. But ignoring that, nothing special would happen. Uranium only yields 20 billion calories per gram when you use it to do nuclear fission, whereas the human body is only able to metabolize and take advantage of chemical energy. And at that, only from a narrow range of carbon-based molecules like sugars, fats, proteins, and ethanol. Move to even slightly different carbon chemistry, and we're no longer able to process it because we don't have enzymes for it. For example, we can't derive energy from drinking gasoline, which is just another bunch of hydrocarbons very similar in concept to fats but with different numbers of carbon atoms in the molecule and without the carboxylic acid group on the end. When we gain weight, it's because the energy-rich molecules we ate have been disassembled and reassembled into body fat. That fat is built out of the same set of mostly carbon, hydrogen atoms as were in the food to begin with. We can't invent new mass or new atoms out of nowhere from hypothetical energy alone. So even if we were capable of metabolizing uranium for energy, the body would presumably store a gram of the stuff as just a small pellet of uranium and then gradually use it up over the course of the next 8 to 10,000 days. There wouldn't be any way to chemically transform it into body fat. There's no uranious enzyme in our bodies to help digest uranium and utilize those 20 billion calories. You wouldn't be hungry ever again because you ate a lot of calories, and also you'd be dead. So the short answer is you'd die. The longer answer is the 20 billion calories figure refers to the energy content when uranium undergoes nuclear fission in a controlled environment, like a reactor or a bomb. It's not in a form that could be metabolized by the human body to extract those calories. Even if you could somehow survive the toxicity and radiation. Your balls would glow at night. Those aren't edible calories. Your body probably wouldn't digest it, but you would get radiation poisoning. You'd be caloritized to death. TLDR. It's released very slowly, about 6 calories per year. But the bad news is that you'll be poisoned by it long before that tiny amount of radioactivity has any impact, though you might not die. 1 gram is the fatal dose for inhalation, 5 grams for ingestion. For naturally occurring uranium, it is 99.3% U-238, which has a half-life of 4.5 billion years. And each decay releases 4.3 MeV, the fast-decaying isotope, U-235, which makes up most of the remaining 0.7%, also has a very long half-life, 0.7 billion years, and emits only a tiny bit more energy, 4.7 MeV. Thus, it's pretty safe to say that it takes 4.5 billion years to release half of this energy. The decay rate is exponential, meaning that the first minute of this 4.5 billion is the most active. In fact, the energy release rate is double at the start than after one half-life. The maths works out as the energy released in the first t seconds for a half-life of t seconds, being lane 2 tt for tt, that is, or 0.7 tt, i.e. 5e19 of the total energy per second. Taking your 20 billion calories at face value, this is 1 times 10 to the 8 calorie per second, or about 3 calories per year. Then, fun fact, I searched before posting this and it turns out that about half of the activity comes from the third isotope, U-234, which makes up some tiny fraction of a percent of naturally occurring uranium. So maybe double this. You would gain 5.7 million pounds smiling face with hearts, smiling face with hearts. This is challenging the nature of the subreddit. Uranus probably will have a hard time. You still wouldn't be as fat as your mom. A question that is a reflection of our education system. I despair.
If you enjoyed this video, please check out our playlists full of similar content. Epic Heracast is like doom scrolling for your ears. Please like, share, and subscribe.